We've had Christmas music blaring at the house all weekend. I love it. And you, oh, you really want to know? Okay. Terrible. Terrible. Yes, more optimization. That was about 2 years ago. All right, designing again. You are designing a 1000. Why is it blinking like that? Watch. Oh, it goes away and then it comes back. Centimeters, goes away, comes back. Cube, goes away, comes back. What? What is that? What is that telling me? Volume. Volume. That's what I was trying to get out. Oh, this is not gonna work. I'm gonna have to end up restarting. There is no waste in cutting the aluminum from the side. This is kind of like what I was telling y'all about that I learned in my linear algebra class. I'm getting real excited. Joyce, stop judging me like that. I can see it all over your face. The top and the bottom of radius R will be cut from the squares that measure R units on 2R units on each side. So let me think about this just a minute. I have a square. The circle is cut from the square. The radius of the circle is R. I have to do this or I can't figure out what I need to do with the problem if I don't have a picture drawn out. The top and bottom of radius R will be cut 2R units on each side. Well, that makes sense. The whole side is 2R, so half of that up would be, y'all okay there? The total amount of aluminum used up by the can will therefore be 8R squared. So what they're giving you here is surface area plus 2 pi RH. Rather than the from example 4, and this is whatever. Okay. Most economical. So if I'm looking for most economical, what am I looking for? Minimum. I'm looking for a minimum. A minimum of what? Area. Yeah. But I'm given volume. So I guess what I need to do is try to write an equation using the volume given. I've got two variables in this area. I've got an R and an H, right? So I need to write that with just one variable so that I can essentially take the derivative. Well, but you have to find that in order to find the ratio of H to R. So you'd need to know what H and R would be in order to write the ratio. Does that make sense? You sure? Remember, a ratio just compares two numbers. So essentially, this is just another way of asking you, what is the minimum height and radius to use the least amount of material? I don't know. Okay. How do you find the volume of a can? And this would be something that would be given to you if you, that's the area. Pi r squared h. This is volume of a can. Pi r squared h. Because I looked it up. That's the volume of a con. They would give you that. The volume of a cylinder is pi r squared h. They'll give it to you on the exam. I don't know why they did. Well, they said reference example 4, and it's given an example 4. That's what I flipped back and looked to make sure I was right. Who knows? All right, so 1,000 equals pi r squared h. What do you want to solve for? H. H, since h is only in there one time, and the other one. So I'm going to divide by pi r squared. Am I losing anybody? Is everybody okay? Did y'all even close to go about this way? From here you can do it. Once you get it down to what that's your key on these is get it down to one variable so that you can take a derivative. We have to restart this because it's been driving me crazy. All right, so this is going to go in for h. Guess I really didn't even need my picture, as hard as I worked on it. 8r squared plus 2 pi r times 1,000 over pi r squared. I'm going to clean this up just a smidge. An r up top and in the bottom, a pi up top and in the bottom. And so my area in one variable would be 8r squared plus 2,000 over r. Can you take the derivative of that? Yes. See what happens. Well, like, she can't. They stole it. Wait, I have to Huh? I know. But now that I'm recording, I don't really know. I mean, I'd have to have 2 recordings. Yeah. Then maybe I wrote it wrong. Did I? Okay. All right, I need a common denominator, right? Because I need to know where this equals 0. But to do that, all right, r squared. So I got 16r cubed minus 2,000 over r squared. It doesn't make any sense to have a radius 0, right? Yeah. Okay, so let's think about it. If the volume is 1,000, it's hard for me to think about the upwards limit right now. I say we solve it, we find what it is, and then we say, does it make sense in context of the problem? They do like the, and they kind of interpret it. And if my brain would think through, well, the volume of a can is, what do we say, pi r squared h, and that equals 1,000. Then r can't be any bigger than possibly the square root, maybe. No. I'd rather just plug it in. And we'll see if it makes sense in context of home. Just, negatives aren't going to work, right? Negatives are out. Zero's out because you're not going to have a 0 radius. You're going to have a can, right? So it's really this equal to 0. So we get 2,000. If I add 2,000 to both sides, divide by 16, and then take the cube root, you're right, it's 5. let's just make sure that that's a minimum. I hope we get negative positive here when we plug in. You're plugging into the derivative to tell what the function is doing. Mm-hmm. Yeah. What do you mean? You would have to test the endpoints. Then we would have to look at where the domain was restricted to see what the endpoints were. These type of problems for right now, you're always going to be right there. The hardest thing about these is you might, if it's a maximum, you might have an endpoint on this end, or if there could be multiple critical points and you have to pick the one that's the minimum instead of the maximum. Similar to, that's fine. We'll look at it though. Oh, you already, okay. And now. All right, so what is 5? 5 is my what? R, right? Because that's what I found. So R equals 5. There's my minimum. Now I need to find which H corresponds to that, right? So I can go back up. I would use this equation where I already solved for H. So 1,000 over 25 pi, which would be, what, 8 over 5? Oh, 8 over 5. You're looking for the minimum dimensions. I mean, you're looking for the dimensions to give you the minimum area. Because remember, that's what's costing you the most, right? It's costing you to make the can itself. So you want to use the least amount of material possible so that it costs you the least amount. And so in order to do that, I need a minimum of the surface area. And they gave me the surface area formula. So that's what I took the derivative of. The hard part about it was because I had two variables going on there and not just one. I still didn't answer the question because what did it ask me? The ratio. It's 40. This is 40 over pi. So it asked me for the ratio of H to R. H to R, which if you remember the way ratios work, you can either do it as a ratio like this, you can do it as a fraction, you can do it as whatever. So H is 40 over pi. This is to 5. And I think that they wrote it a little bit differently in your book. So they divided both of these by 5 to understand that if you do 40 over pi divided by 5, right? Because that's what a ratio is. This is like 40 over pi times 1/5. That gives me a 1 for my h and a 8 over pi for my r. So 8 over pi to 1. Either of those. This is just, this goes back to whatever grade you worked with ratios. I don't remember what grade that is. This is just an unsimplified ratio. This is a simplified ratio. That's all that is. Doesn't seem that bad. What you mean? Which part? 40 divided by 5 is 8, right? Well, we just did this is exact. Well, you want to leave the pi in there because then you get. I mean, technically, I guess not. What'd you get? 2.546. You did 40 divided by pi. Okay, 1,000 divided by 25. 25 pi divided by 5. 25.1327. 40 divided by pi. I did 1,000 divided by 25 pi. Oh, I bet you didn't put parentheses in there. You do 1,000 divided by parentheses 25 pi. Okay, 12.73. And then what are you saying? Oh, and then you divided it by 5 again. You got 2.546. Yeah, that's the same thing as 8 over pi. Yeah, same thing. Yes, no, maybe so. Depends on this related rates thing that I'm doing. I got to show you linearization, but it's the same. But I got a couple more optimizations. I know. Yeah. Well, up to y'all. We'll do it in class if we do it. I'll let you know tomorrow for sure. This stuff in here is just extra stuff. A 24 by 36 sheet of cardboard. I gotta see it. Is folded in half to form a 24 by 18. Okay. Rectangle as shown in, oh, there's already a figure. Then 4 congruent squares of side. This is just like the ones where I was showing you about taking off the sides. So we're going to call it X because it's the same amount each and every time. Let me hook up my camera. It's just going to lag my computer down even more. Okay, that heated. It was 58 degrees when I came in here this morning. All right, let's look at it. It's nice when they give you a picture. All right, so the first ask, and you have to kind of visualize this being folded up into a box. So as opposed to the box we talked about Friday, this box does have a top to it, right? So it's folded over so that it forms an enclosed box. All right, so the first thing is the volume. Well, we know volume is length times width times height, right? So how am I going to figure that out? What do y'all think? All right, look, they've got the base here for you, right? I know that these, let's talk about these dash lines first. How long are those dash lines right here? Because those are kind of the easiest to find. 24 minus 2x, I agree. Okay, that's each of them. That's the length. So how about the width? What did you get? 36. All right, so this is my length and this is my width. Do you agree? My height should be x. This should be the same for my height, right? What is this corresponding to? Is that also my? That's what I was thinking. Because they folded it in half like this. This is an x and this is an x. So this is 2x, right? That's the base. So my base, so I'm 24 minus 2x by 2x. Is everybody okay on that, at least for the base part? Now how about the height? We're finding the volume, so we need the length, the width, and the height. Okay, so I looked at the base since it's a rectangle. So I've got length, that's 24. This is 24 minus the 2x's on the side. The base, the width here of the base is 2x. But now I need how high up it goes, like what it spans. So what are we going to use to find that? So let's see. The base is this area right here. I mean, the height. This is my height, right? If it's folded up, you agree? Envision this folded up. It comes up. This is half of the top piece. This is half of the top piece, right? So what is this length? Well, it was 36, right? Half of it, you're right, was 18, but I took off an x and an x, so the height is 18 minus 2x. That makes sense to everybody. Was the problem with this one coming up with those, or was it the whole thing? So for volume on this one, I would say volume equals 24 minus 2x times 2x times 18 minus 2x. There's my volume. That's part A. Find the volume. Is that what you got, Robert? Said you love this kind. Find the domain and graph this. Okay, we're not going to graph it, but we will talk about the domain. X can't be any smaller than what? 0. I know I'm between 0. Now, if you think about this one, it's a little easier to think about the domain. So take the shortest side that you have. What's the shortest side that I was given? 18, right? Because I've cut in half, yes? So this is 18. And from that 18, I take 2 x's off. Okay, well, whatever. Yeah. Sorry. But from that, I take off 2 x's, right? Smallest side taking off 2 x's. So I know that x can't possibly be any bigger than what? $18 minus 2 x's. It can't be bigger than 9, right? Because this has still got to stay bigger than 0. I've got to have something there. So if I solve that, I know that it's got to be bigger. So I'm between 0 and 9. If you let x, right, if you got to take 2 of them away and both of them are 9, you don't have anything left. Because, right. So I would say that's your domain there. You okay with that? Find the maximum volume and the value of x that gets it. So this is straightforward. There's no other equation to use to plug into to solve for. I'm just going to find the derivative. If I'm, yeah. It's no, it's going to be. Because you can't be 0 or it wouldn't be taking anything off, yeah. I would probably multiply this out to get a polynomial to then find the derivative of. Or if it was, is this a calculator problem? Well, I guess you still don't know. I could graph the derivative. We've talked about graphing the derivative before, right? It's a handy little tool to have since y'all are good. I'll take just a minute since y'all are. Do you remember how to graph the derivative? Yep. Go into y equals math and derivative. Now remember, mine looks a little bit different than yours. I'm going to type my equation in here. So what did I have? I had 24 minus 2x, 24 minus 2x times 2x times. Yours might look a little different. You still need to put the equation here. You do it with respect to x at x. So you do double x. You don't have that. Who's got one that doesn't look, that I can, here, you want me to put it up here so everybody can. So if yours looks like this, terrible glare. Just type the equation in here. So what we have? 24 minus 2x, 2x, 18 minus 2x, and just have x equals x instead of x equals a number. That lets you find it for every x instead of just and then hit graph. Sim 6 is what I'd probably start on. Remember what we're looking for. You probably typed something wrong. I should have a 0 somewhere. Remember, I'm only between 0 and, I've already set my domain, right? From 0 to, what did I set it to? 9. So I'm only in between here. I just need this 0. And I can clearly see that the derivative is negative and positive. It changes signs. If it goes from negative to positive, then I definitely have a minimum here. So I'm just going to calculate this 0. This is an excellent technique if it's the calculator portion. Let me see where you messed up. Oh, you got to finish with comma x, comma x. Second trace. And your notebook too? I wonder if it's all wet in there. That's awesome. If they can see their face clearly enough, that's the problem. To identify them. Which is probably dark because it gets dark at like Robert's second time.
That would, if you eat that McDonald's, that would be worse than I would ever had.
Okay. $3.39. The nice thing about using your calculator to do this, and the more proficient you are, I know I stress a lot of non-calculator stuff because there's a whole half a test without it, but there's also a whole half of a test with it. So once you master doing it without it, it's good to know how to go back and do it with it because it's a real time saver. If you had to do that by hand, gross, right? But that was really quick. I know it's a minimum because I can look at the graph. I don't have to show anything because I can just pull it from the graph and know that that's a minimum. The gross version. And that probably took a really, really, really long time, right? It's going up. Yeah. This is not the function, this is the derivative. This is, it's really, really, really a good tool to have because they'll throw these kind of questions on the multiple choice, but the calculator part, and if you don't know how to use your calculator, you'll get bogged down for 20 minutes and waste your time trying to solve this one. When it should be a, right. Huh? Yeah, so I'll do it again for you. Watch your X values and Y values there. Whenever you go second trace, hit 0. Oh, did your mom order another calculator? Because she texted me and asked me what time. All right, left bound. Watch these numbers so you know where you are. If you can't ever find your spider, especially that Y value, whenever it first started, um, you see how high up I am? I'm at 659 on Y. I'm only at a half X, so I'm somewhere over here, way up in like Never Never Land. But if I hit enter, that tells me where I was. I'm going to keep going right, but I got to go a long time, and I might be going, but oh my goodness, where is he? I can't see. Well, he's still at 200. So I got to keep going, because remember, I got to cross over from positive down to negative. I'm still at 100. I'm at 36 now. If I keep going, oh, just pass by in one blink. There he is. And it doesn't matter where I could go from there. It doesn't matter. And hit enter to get that value. Yes. It's not quite as hard as this one. That one is just, I'll show you the picture. I'll set it up and show you. Yeah, setting up's the hardest, I think. That's why I always draw a picture. All right, so then I plug that one back in, and I plug it back into the original equation, right, to find the volume. Is that what it asked me, or did it ask me for dimension? That's it. I think that's why they asked you about the graphically, too, because, and you don't have to write a paragraph. What'd you say, 7? Set up for 7? You're planning to make an open rectangular box from an 18 by 15, or an 8 by 15, excuse me. So 8, yours is not lopsided like mine. 15, cutting congruent squares from the corners and folding up the sides. So for this one, my length is going to be, and if these are all x, 15 minus 2 x's. My width, 8 minus 2 x's. And then my height is just that x that I took out, because these sides fold in. These are the x, they fold in, and the height is going to be that part that I took off. So my height is just x. Anything else? The same way your book does, because I think they complicate it. I think it's not as hard as what they make it. Here's linearization in a nutshell. They take a really complicated function, okay, and they ask you to write a linear approximation and use it to find a certain value. So in other words, maybe they give you like, maybe they give you something like f of x equals cosine x. And they want you to write this linear equation that will kind of represent the function at a certain area. And then they'll give you an x value. And then they'll say, use your linear equation to estimate when x is 1.75. Because if you just plug 1.75 in here, it would be hard for you to find a value at 1.75, right? What is the cosine of 1.75? Don't know. All right, so here's what we're going to do. The directions would say, find the linearization at x equals pi over 2. And use it, so we want to linearize that, and use it to estimate or approximate the cosine of 1.75 without a calculator. First thing I'm going to do is write the equation of the tan line at the point given. That is all linearization is. That linearization is literally the equation of the tan line, because if I've got this whole, like, cosine looks like this, and here's, let's say, cosine of pi over 2 is 0. So let's say here, and they want me to estimate some stuff. Well, I can do this tan line here. Now, the further away I get from the tan line, the less accurate my estimation is. But because this is a line, I can do that without a calculator. I can easily plug things in without a calculator because it's linear, right? MX plus B. Yes? It's a lot easier to plug it, so yes, because it is. Y'all don't want to know why, you just want to know what to do, don't you? Okay. Okay. So I'm coming up with this equation, and then I'm going to use that equation, and instead of plugging into my original and saying, what's the cosine of 1.75, which I can't do without a calculator, I'm going to find the equation of this line, and then I'm going to plug 1.75 into that and get an approximation. Depending on how close I am to pi over 2, depends on how accurate my approximation is. Okay? So what's the equation of the tan line? Is that what you're asking? Yes, yeah, yes, it's negative sine. But because I'm writing the equation of a tan line, I'm doing this so that I have the slope, right? The slope of the tan line is going to be the derivative at pi over 2. Agree? Which is negative sine pi over 2. Yes? What's the sine of pi over 2? It's 1, so it's negative, so it would be negative 1. Okay? I still don't have an equation for a tan line. I've got a slope. I need a point and a slope. So how do I get the point? Pi over 2 into the original equation, right? F of pi over 2. So the cosine of pi over 2, which is 0. Now this is set up to be easy for you because they're giving you the x at which you should, and for this one they always will be. Okay, so I'm going all the way back to like unit 2 where I wrote equations of tan lines. It said, that's given in the problem. This is the problem that's given to you. These are the directions. If this equals this, estimate cosine using linearization. And no calculator. I'm still writing the tan line. So remember, for a tan line, you need a point and a slope. The slope is coming from the derivative, yes? The point is coming from whenever I plug into the original.
Okay, so the F of pi over 2 is
yes. So this is my point. This is my slope. So y minus 0 equals slope times x minus pi over 2. So now there's only one more step. Yeah. Use your tan line to estimate. To estimate what? Well, they asked me. They said, estimate the cosine of 1.75. So this is my tan line, right? They're asking me for cosine 1.75. So I'm literally plugging 1.75 because my original function was cosine x. So I'm plugging in 1.75 for my x here. In your new equation, yes. And since they said no calculator, I would do this. And I would stop because I have no idea what pi over 2 is. I know it's half of 3.15, so maybe about 1.75. So close to 0.
So you just plug it in.
No, just because that's what I'm trying to. If you look back at the way it was written at first, my f of x is cosine of 1.75. And I'm approximating when x is 1.75, right? Like this is my function is cosine x. I'm approximating this, so I'm using it to approximate when x is 1.75. Does that make sense? Yeah. It's really not hard. Huh? This gives me an approximation. All right, so do this. If you put this in your calculator, what is, and this is not a calculator problem, but just to show you, pi over 2 plus negative 1.75. I get, I got one negative, oh, point. I'm reading upside down. I was like, there's no way. Negative 0.179 is what I get here. If I go back to the original equation, remember that original equation was just f of x equals cosine x? What is f of 1.75? So use your calculator to do cosine 1.75. If you borrowed one of mine, make sure your mode is right. I got negative 0.178. Look how close they are. It's an estimation. That's exactly right. No, I'm just showing you. Huh? Yeah, you can. Yeah. Yeah. Because remember, I'm using the tan line is just an estimate. The actual value sits on the curve itself, and the further away you get from this point of tangency, the less accurate it's going to be. Yeah, but I put that on my calculator and got that. Negative 1.75 plus pi over 2. That's where I got confused too because I didn't see the point in it. Yeah. All right, I'm not going to go much further than that because I don't really need you to know much further than that. That's about all I need you to know with linearization. So let me show you what I want you to do. So pretend